In this lesson, we're going to be learning how to solve polynomial and other nonlinear inequalities. Before we do, I'd like to recall how to solve a linear inequality, which is simply an inequality that has a linear function on one side. So in these situations, when we are not solving an equation equal to a certain number, and instead we have an inequality symbol, we can solve the inequality in a very similar way to solving the corresponding equation, which is just isolating the variable on one side. So notice the first step is to subtract 1 from both sides, giving me negative 4x is less than 8. Now, in order to get x by itself, we still divide by negative 4. And you might recall that when you divide two sides of an equation or multiply two sides of an equation by a negative number, you have to switch the direction of the inequality sign. So this less than symbol now becomes greater than. So if you think about x being greater than negative 2 on a number line, that would give you all of the values from negative 2 to infinity, not including negative 2. If it said greater than or equal to negative 2, then we would put a bracket on the negative 2. Unfortunately, if the inequality is not linear, then we can't isolate the variable on one side like we were able to do right here. So instead, we have to look at a different process. So let's take a look at this inequality. Here we have a polynomial on one side is greater than 9. More specifically, it's a quadratic function. And so now we're trying to find out, when is this quadratic function greater than 9? So we can't actually just move everything over and isolate the x on one side. So instead, we're going to set the inequality to 0 and solve it in a very similar way to that we would have solved a quadratic equation. So if we subtract 9 from both sides, that ends up giving me x squared minus 2x minus 8 is greater than 0. Now, if that was an equal sign, we would apply the zero product property by factoring and setting each factor to 0. So in fact, that's exactly what we're going to do. We're going to find the critical numbers of this inequality, which are actually just the values that make that corresponding equation equal to 0. So the first step is to factor the polynomial. And now, instead of thinking of it as an inequality, why don't we think about it as an equation? When is x plus 2 times x minus 4 equal to 0? So by the zero product property, we just set each factor separately equal to 0. And therefore, our values for our critical numbers are x equals negative 2 or x equals 4. So we should note that those are the only two x coordinates that will make this quantity equal 0, or that will make this function equal 0. That must mean that every other x value that I plug in is either going to make the function positive or it will make the function negative. And that's what we're after when we're solving an inequality. So what we're going to do next is place the critical numbers in order, by the way, on a number line, and choose choose a test value in each of these intervals. So if we put negative 2 and 4, you might notice that we have 3 different intervals: an interval that occurs before negative 2, an interval that occurs between negative 2 and 4, and an interval that occurs after 4. So if we were to choose some random x coordinate that's before negative 2, perhaps we choose negative 5, the best thing to do is to plug that x value in to the factored form of our equation, not in the original form that's unfactored. The reason for this is if I plug in negative 5 to factored form, all I'm trying to figure out is whether or not this x value will give me a positive answer or a negative answer. So I should be able to see, without actually solving or calculating the values, we can see that negative 5 plus 2 gives me a negative number. Negative 5 minus 4 also gives me a negative number. And if I multiply a negative times a negative, I get a positive value, which is why on our number line, we simply put a positive in the region before negative 2. So now let's pick something between negative 2 and 4. Note that anything we pick is going to have the same sign, because there's only one way to change from a positive to a negative, or vice versa, and that's by passing through a value that gives me 0. since -2 and 4 are the only locations where the function is equal to 0, that means that everything between -2 and 4 will have the same sign. So why don't we try x equals 0? So if I plug 0 into factored form, I get 0 plus 2 times 0 minus 4, which of course gives me a positive value times a negative value, which will always give me a negative output. So I now put a negative sign in between -2 and 4. Lastly, I just got to pick something larger than 4. You can pick virtually anything you want, so let's try 20. If I plug in 20 to the factored form of the equation, we get 20 plus 2 is positive. 20 minus 4 is also positive. And if I multiply two positives, I get a positive, which finalizes my number line. Now, the way that this helps us is because looking back to my original inequality, once it's greater than 0, I now just have to figure out what intervals I'm interested in. So in this case right here, when you see greater than 0, you should realize that any number greater than 0 means positive. Any value that says less than 0 means negative. So I'm trying to find out, when is this quadratic positive? Well, since I have my number line, I can see the intervals where the values are positive. So I know that that's going to occur everything before -2, which is -infinity to -2. And I also know that it's going to occur where the value is also positive, which is greater than 4, or rather 4 to infinity. Now, the last thing we have to check is to make sure we're using our brackets or parentheses correctly. And since this inequality simply said greater than 0 and not equal to, that means that we're not going to include -2 or 4, since those values made the function equal to 0. So let's take a look at another situation by comparing two rational functions. If I now want to divide or find an inequality or find the solution to an inequality of two rational functions, you may think that we could do this in a very similar way to where we would solve a rational equation. Remember, the rational equations are solved by cross-multiplying x times x plus 1, and then cross-multiplying 1 times x plus 9, setting them equal and solving. Unfortunately, we cannot do that when it comes to inequalities. We have to do the same process we did before, which is setting the inequality equal to 0. And the way we do that is by subtracting the quantity on the right onto the left, so that now I have some function is greater than or equal to 0. We're going to combine these into one single rational function, but the only way to subtract fractions is to get a common denominator. So we need to make sure to multiply the numerator and denominator by whatever factor is missing. So here we had an x plus 9. This denominator over here needed an x plus 9, so we multiplied numerator and denominator by what was missing. We could see the denominator on the right was x plus 1. We needed an x plus 1 on the left fraction, so we multiplied numerator and denominator by x plus 1. Now I'm going to keep the denominator in factored form, but we're going to expand the numerator because we have to somehow combine these into one single fraction. Now that the denominators are the same, we can combine them into a single fraction by just taking the numerator of the left fraction and subtracting each term in the right fraction. Notice that that causes the x's to cancel out, therefore giving me x squared minus 9. And then my last step is to factor what remains, and we get x minus 3 times x plus 3 in the numerator because of the difference of two squares. So now we have a slightly more complicated function on the left side, but I can still see that it's set to 0, so I still want to find my critical numbers. So recall the critical numbers are found by setting the function equal to 0. We should realize the fractions are equal to 0 when the numerator is equal to 0. So two of my critical numbers are 3 and -3. But there was another type of critical number, as we saw on the previous slide, that said the critical numbers could also occur when the function is undefined. We know that fractions are undefined when the denominator is equal to 0. So I also see two more critical numbers of negative 9 and negative 1. Now that we have each of our critical numbers, we could put those critical numbers on a number line and do the same process that we did before by picking test values. But now we're going to plug it into the factored form of this fraction, and therefore pick something before negative 9, like negative 10. Now notice, by plugging negative 10 into each of the four factors, we should be able to see whether or not that negative 10 is going to cause the factor to be positive or negative. As you can hopefully see here, each factor will become negative if I plug in negative 10, and therefore a negative times a negative is positive. A negative times a negative is again positive. So if I divide a positive by a positive, I get a positive result. Note that I don't have to find the actual value that we get when we plug in negative 10. We actually don't even care what the value is, because we know that everything before negative 9 will give me a positive output. So now let's pick something between negative 9 and negative 3. I chose negative 6. So notice that negative 6 is still going to make the first factor on the top negative, the second factor on the top negative, the second factor, and the denominator negative. But notice that when I plug in negative 6 to x plus 9, I get a positive result. So now the only thing that changes is that I get a positive divided by a negative, which makes the whole output negative. So we know that every value between negative 9 and negative 3 is negative. So we can pick something between negative 3 and negative 1. Let's try negative 2. And going through the same process, we plug in negative 2 to every factor and realize that the top right will give a positive value, the bottom left will give a positive value. So now we get a negative value in the numerator, a negative value in the denominator. So when I divide a negative by a negative, I get a positive, which is why we can fill in a positive to the next region. Next, we can pick something between negative 1 and 3. Again, I like to choose 0. So when I plug in 0, I get a negative times a positive over a positive times a positive. And when you think about it in this way here, that means we get a negative value divided by a positive value, which is finally a negative value. Fill in a negative in that interval. We've got one last interval. Pick anything you want that's bigger than 3. Why don't we pick 4? If I plug in 4, notice that that's going to now make every single factor positive. When I take a positive divided by a positive, I get a positive. And now that our number line is complete, we're ready to write the intervals that make the inequality true. Notice that because this inequality says, where is this function that we just tested, where is this function greater than or equal to 0? Greater than 0 means positive. So we're going to fill in all the intervals where I see a positive sign, which is before negative 9, between negative 3 and negative 1, and after 3, or rather 3 to infinity. Now you can see that a bracket was put on all of these values because of the fact that we saw an equal sign. And that's what numerous students would do if they were to try to solve this inequality. Seeing an equal sign, they just put a bracket everywhere. But keep in mind what a bracket means. The bracket is saying that this function is either greater than 0 or equal to 0. When I go back to my critical numbers, notice that only 3 and negative 3 caused the function to equal 0. Negative 9 and negative 1 caused the function to be undefined. So I can't include the x values that would cause undefined. So we have to be very careful that the critical numbers don't make the denominator 0, and therefore I have to modify my interval to put parentheses on negative 9 and on negative 1. And so in order to solve any nonlinear inequalities, the process that we can take is to set the function equal to 0, find your critical numbers, and when you put those critical numbers on a number line, you can find test values that'll allow you to find whether or not the function is positive or negative, and lastly refer to the inequality sign to determine whether you're looking for positive answers or negative answers.